Hello, dear students. In the previous lecture, we were studying about the reciprocating compressors. So, in the next chapter, this current chapter, we will be discussing or we will be coming to know about the working and applications of rotary air compressors. Now, in the first part of the rotary type of compressors is your positive displacement compressors. The positive displacement compressors, and they are basically continuous air supply compressors. They have the usual construction. In the usual construction, they have a rotor and the casing is there. So when the air is trapped between the rotor and the casing and the volume is reduced, this reduction in volume results in the increase in pressure of the air. So that's why they are known as positive displacement compressors, because in the positive displacement compressors, we are able to visualize that actually some volume of air is getting reduced. And because of this reduction in volume, the static pressure of the air increases. Now, if we look at the classification part, the rotary air compressors, they can be subdivided into two categories, that is positive displacement compressors and dynamic compressors. Okay, the positive displacement type of compressors can again be classified into three types. The first is your roots blower, second is your vane type compressor, and the third is your Lysholm or the screw type compressors there. Okay, in the dynamic compressors, there are two types, that is your centrifugal compressor and the axial flow compressors are there. So this is the classification of the rotary air compressors. Now, in the consequent slides, we will try to learn about the working and construction of each and every of these types of compressors. Okay, the first type of compressor, that is the roots blower. Now, in the roots blower, as you can see in the diagram, there is this is the outer casing is there, the hatched. This is the outer casing, and inside you can see two lobed shapes. These are dumbbell-shaped, lobed-shaped rotors are there, and these lobed-shaped compressors, the profile of these compressors is made cycloidal or involute. So this involute or cycloidal shape of these lobes is made in such a manner so that at each rotation point, the lobe or the internal lobe, it is in contact either with the casing and with the other lobe. So there is always a pocket of air that is there on each side of the lobe, and it is always in contact on the opposite sides to either the casing or to the other lobe. Now these lobes, one of the lobe is attached to the shaft, and this shaft is connected to either a motor or an engine, and one of the lobes is the driver, and the other lobe is connected with the help of gears, and the other is driven. So if one is you can see that this one, if it is rotating in anti-clockwise direction, the other will be rotating in the opposite direction, that is in the clockwise direction. So both the lobes, they rotate in the opposite direction. Okay, so if we look at this is the actual diagram, a 3D cut view section of a uh, roots blower. Okay, so here if you can see there are two lobes inside, and one of this lobes is connected with this shaft, and this shaft is connected to a motor. So this is the driver, and at the back you can see that there are two gears are there. These are helical gears. With the help of these gears, if one rotates in the clockwise direction, the other will rotate in the anti-clockwise direction. So one is the driver and other is the driven. Now we will see about how this type of compressor is used to compress air. Now in the working part, you can see here, this is the working from A if you see in the B part, when the lobes they are in this position, so the bottom is the air inlet and the topmost is the exit or the discharge port is there. So in this when this position of lobes is there, so the inlet port is open and the air can be sucked inside through the inlet port. Okay. After that, if you see at again the lobes when they rotate, the position changes, and in the D part you can see that the air gets trapped between the outer casing and this left lobe. Okay. After that, when the uh, arrangement reaches figure E, in this arrangement, the discharge port is open. Now, the pressure of the air in the air that is trapped between the lobes is the atmospheric pressure, and the pressure on the discharge side is the discharge pressure. So the discharge pressure is greater as compared to the air that is trapped between the lobes. So what happens is the backflow of air takes place. So high pressure air starts to come inwards, and in this process it compresses the air that is trapped between the lobes. So this high pressure air, when it moves inwards, it compresses the air in this process. So when after that, because these lobes they are rotating at a very high speed, so this air is pushed when the pressure becomes equal. This air gets pushed towards the outer side. Okay, and then again we come back to the figure B, where again the you can see here at F what is happening is again B and F figures they are almost the same. Again what happens is the space is open and the air comes in, it gets trapped like in figure D, and then again backflow of air takes place, and the high pressure air it compresses the low pressure air, and then the because the lobes they are moving at a very high velocity with the help of a motor, this high pressure air is thrown inside the discharge pipe and into the collection tank where the compressed air is collected. Okay. So here if we look at the working part, the rotation of the rotor creates a space. This we have seen in figure B. Then the flow of gases in the casing space continues till both the rotors change their position, as in figure C is there. Uh, the air gets trapped in the rotors and the casing. The trapped volume of air is not internally compressed. So here the compression is not taking place internally. It is only displaced at high speed. So at very high speed, because the lobes they are moving at a very high speed, the trapped volume of air it is displaced at a very high speed from suction side to the delivery side. Okay. Since the compressed air is so when we are here, see now the discharge side the pressure is high. Okay. So the when the rotors uncover the exit port, some pressurized air it enters into the space between the rotors and the casing. This process is known as the backflow of air. Okay. Now this backflow of air it compresses the air, and then this high pressure air is thrown or it is thrown into the discharge side. So this is the working of the roots blower and how the air gets compressed inside this. So here you can see the animation of the working of a roots blower. So the blue side is the inlet side, and you can see that the air gets trapped inside this section, and as it moves it opens the discharge side. The high pressure air it flows backwards, and it compresses this blue air and it becomes red. So the red is your high compressed air which is at higher pressure. Okay, so you can see that in this motion at the same time you can see that the air is getting trapped onto the other side also. So we are getting a continuous supply of air from both sides of the lobes. So as in the case of a reciprocating compressor that we have discussed in the last chapter, where the suction takes place and then the compression takes place and then the delivery takes place. So again the suction takes place, compression takes place, and delivery takes place. So the air supply is not continuous in a reciprocating compressor. It is in the form of pulses. But in this roots blower, you can see that the supply of air is continuous. Okay, so there is no pulsations here. So that is one of the advantages of using rotary compressors as compared to the reciprocating compressors. Okay, is this clear to all? Okay. Now next, if we see here, there is another this on the in the top diagram. You can see this is your two-lobe compressor, and in the bottom you can see there is another type of compressor in the roots blower. It is your tri-lobe compressor, where there are three lobes on a single rotor. So 1, 2, and 3 lobes, and on the other side also there are 3 lobes here. So more if we want to have more supply of air per unit time, so we can use this tri-lobe compressor, where if you want more meter cube of air per second. Next is we will see look into the analysis part. Okay, now the process of compression can be represented by a constant volume line. Now because when the backflow of air is taking place, the compression of air is taking place, and we are not here, what we are doing is, in this roots blower, we are not actually reducing the volume of air. So the compression of air is taking place at constant volume. So on a PV diagram, the process can be shown from process 1, that is the initial state, where the volume is V1 and the pressure is P1. This is your atmospheric pressure P1, or the ambient conditions here. And from 1 to 2, it is a vertical line. So if it is a vertical line, so this means the volume V1 at point 1, the initial state, and the volume V1 at the final state, that is state 2, is constant. So the volume is not changing, but the pressure is increasing from P1 to the delivery pressure P2. So this is your PV diagram for the compression process inside a roots blower. Now, considering the volume V1, now if we, because this roots blower, it is a open cycle. Okay. Now, for an open cycle, where the mass is flowing in and out of the system, for an open cycle, the work done is given by integral minus VdP is there, where V is the volume of air and dP is the change in pressure is taking place. Now, for this particular compression process inside the roots blower, the volume is constant. So if the volume is constant, this volume can be taken out of the integral. So V1 is constant and integral dP is P2 minus P1. So hence the work done for a constant pressure compression inside the roots blower, or the actual work done, it is given by V1 into the change in pressure, that is P2 minus P1. Now, if this compression for the ideal case, if this compression is taking place ideally, or if the compression is taking place, say, isentropically, we can say, where the entropy of the system remains constant, in that case, the isentropic or the ideal work will be given by gamma upon gamma minus 1 into P1 V1 in multiplied by, inside the bracket, it is P2 by P1 to the power gamma minus 1 upon gamma minus 1 is there. Now this equation we have derived in the first chapter, that is in reciprocating air compressors, where the isentropic work is given by this equation. So we have now the ideal work done and the actual work done is there. Now if we want to calculate the efficiency of a roots blower, now that will be given by the ideal work or the adiabatic work input divided by the actual work input. Okay. So from the above equations, adiabatic work input, this is given by this equation, and the in the denominator we will have the actual work input. Now actual work input, as we know, it is given by V1 into P2 minus P1. We have done it, seen it in the previous slide. So this equation is your roots for the isentropic efficiency of a roots blower. Now if we replace P2 by P1 by pressure ratio Rp, So the equation modifies to this equation here. It becomes gamma upon gamma minus 1 into rp to the power gamma minus 1 by gamma minus 1 divided by rp minus 1. So this is the modified equation for the isentropic efficiency of a roots blower. Okay. Now the efficiency of a root blower, it decreases with the increase in pressure ratio. Okay. It is obvious from this equation here. Okay. So if the value of rp, if we increase the value of rp, the efficiency of the roots blower decreases. So mean to say that now this compressor is suitable for pressure ratios from 1 to 3.6. So 3.6 is the maximum where we can achieve a pressure ratio. Pressure ratio is that is P2 by P1. Okay. So beyond that, if we go for higher pressure ratios, the efficiency of this roots blower, it decreases. Okay. Okay, next is your vane type compressors. Before we go any further, any queries? Okay, next is our vane type of compressor. Okay. Now in this compressor, if you can see this diagram, if you see the black is the outer casing of the compressor, and in this we have a circular drum. If you can this see this purple part is the circular rotor or the drum inside, and in this drum you can see that these are the hollow grooves that are carved inside this drum, okay, or the rotor you can say, and in this in these grooves rectangular plates are inserted, and at the bottom of these rectangular plates there are springs here. Now these springs, they always push the plates, these green plates, in the outside direction. Okay. Now the center of the casing and the center of this drum, they are not same. They are, so you can see that this drum is touching at the bottom with the casing, but at the top it is at a certain distance. So there is some space up there. So this means that the centers of the circular casing and this drum or the rotor drum, they are not having the same center. So this drum is placed eccentric to this casing. Okay. Now, by doing this, what happens is as this drum starts to rotate, okay. Now these vanes, when they are uh, in the bottom position, so in that case, what happens is the casing is in touch with the drum. So this green plate, it is totally inserted inside. Okay. Now, as it moves, if we move towards the top in this direction, so here the spacing, as it increases, the spring at the bottom, it pushes the plates outwards. Again, if we go at the top, the spring at the bottom, it pushes the plate in the outward direction. Okay. Now you can see that there are between these, there are two plates. Okay. Between these two plates there is this pocket that is created. Okay. Now these pockets, what they do is, now in this position this pocket is open to the inlet port. So there is, this is the inlet port, and on the other side this is the outlet port is there. Now this pocket is open to the inlet port, and the air from outside, it comes in and it gets collected inside this pocket. Now as this pocket moves in the clockwise direction, the air then comes in this position where the air gets collected again. If it moves in the forward direction, here you can see that the volume starts to decrease. Now as the volume decreases, the pressure starts to increase. So the air, the pressure of the air, it increases. Further, when it moves further in the clockwise direction, the outlet port, it starts to open, and this air that is partially compressed because due to a decrease in volume, now comes in contact with the high pressure air on the delivery side. Now this high pressure air, it moves backwards, or backflow of air takes place, and the further compression of air takes place because of the backflow of the high pressure air on the delivery side. So partly, so in this vane type of compressor, if you see, the compression of air is taking place partly in the form of compression because of reduction in volume, and partly in the form of backflow of air. Okay, so here this is the description of the working. This is the same that I have just discussed. As the drum rotates, the volume V1 at atmospheric pressure P1 is trapped between the vanes. Air gets compressed due to two operations performed on it. First, the compression takes place due to decrease in volume between the drum and the casing. Okay, uh, during this the compression follows adiabatic compression. So the reduction in volume, the pressure increase due to reduction in volume is carried out, we assume that it is carried out adiabatically. Now the second portion of the compression, the air is compressed due to the backflow of the compressed air. This backflow of air takes place from the delivery side. Now the delivery side pressure is higher than the compressed air, and because of that the high pressure air starts to move inwards. Okay, now the air now gets compressed at constant volume. Now this backflow of air, this compression is assumed to be taking place isochorically. Isochorically means the volume is not changing. Okay, here you can see the animations where you can see the working. There are two types of you can see here the comparison between these two types of vane compressors. This has three vanes, the one on the left hand side, and the right hand side, this you can see it has six vanes here. Okay, so depending upon the amount of air per unit time, the volume of air per unit time we need, and the amount of compression that we need, we can increase the number of vanes. Okay, now here you can see from the left hand side the air is coming in and it gets getting trapped inside this. Okay, and as it moves in this direction, it gets partly you can see that the volume decreases and the pressure increases, and as it moves and it comes in contact with the delivery side, the compressed air, it backflows and the compression of air takes place and the delivery is done. Okay, so this is the working, and on this side here again you can see that small pockets, volume getting decreased and the pressure is increasing, and the supply of compressed air on the delivery side is taking place. So this is the working, construction and working of the vane type of compressor. This is the actual 3D. You can see the actual diagram of a vane type of a compressor is there. So on the left hand side, you can see that this is the circular drum is there, in which the rectangular grooves are cut. And in these rectangular grooves, you can see these plates are inserted. And these cast iron rotor is there, and the vanes, they are non-metallic vanes. Okay. So non-metallic vanes are used because they produce less friction. Okay, and on the diagram on the right hand side, you can see that the inlet port is there. This on top is the inlet port from where the air goes in. It occupies this space in between the two vanes. Okay, and then as the rotor rotates, it gets compressed and is delivered into the delivery side. Now you can see that the inlet area is larger, where the air is getting inside the compressor. This area of cross section here is bigger as compared to the area of cross section at the discharge side. Okay, now discharge side, you can see that this area of cross section is very small. Now this is because it has to accommodate lesser volume of air, because the air has been compressed, its volume has been decreased. So the area of cross section at the discharge side is less, because it has to accommodate less volume of air. But in the inlet port, we want to suck inside maximum amount of air, so that maximum amount of air can come inside and it gets compressed. So that's why the inlet port, the area of cross section at the inlet port is larger, or the inlet port is larger, and the discharge port is smaller. Okay, so this is the main reason of working. Now this rotor, it gets its power from a motor at the back. Here a motor will be installed. Okay, and this motor is connected to a shaft, and then this rotor or the drum, it rotates. It gets its power from the motor, electric motor. Okay, this is your vane type of compressor. Now the analysis part, if we look into the analysis part of a vane type of a compressor, so here the compression is taking place in two parts. Okay. Now this is the starting point from where the volume is V1. Now the pressure is P1. Is there. P1 is the atmospheric pressure. V1 is the volume of air that is sucked inside the vane type of a compressor. Now the compression is taking place, hence the volume is reducing. That is why this graph, the process moves in the backward direction. Now by moving in the backward direction, you can see that the volume reaches V2. Now V2 is smaller than V1. So the compression of air is taking place. Because of this reduce in volume, the pressure increases from P1 to P2. So pressure increases, volume decreases. Now this compression is because the trapped air is being compressed against the casing. Okay. Now this compression is a parabolic curve, and it is assumed that this compression is adiabatic, or the no heat loss is taking place. That is the adiabatic process where the heat loss is zero from the system. Okay. Now, the second part of the compression, that is from pressure P2 to P3, this is because of the backflow of air from the discharge side. Now, this compression is a vertical line, that is the volume remains constant, that V2 is the volume. So, V2 at this point is equal to V2 at this point. So, volume is remaining constant, but the pressure is increasing from pressure P2 to P3. Okay. So, hence the compression is taking place into two parts, adiabatic, and after that it is isochoric. Okay. Now work input for adiabatic compression, this work 1 to 2 process, that is the first half of the compression, it is given by this formula. As we know, it is gamma upon gamma minus 1 P1 V1 bracket P2 by P1 to the power gamma minus 1 upon gamma minus 1, brackets closed. So this is the equation for the work done for the first part of the compression, that is from pressure P1 to P2, this adiabatic compression 1 to 2 process. Second part of the compression is constant volume compression. So it is work from point 2 to 3, that is pressure P2 to P3. So in that case, we know it is given by integral VdP. So volume is constant, so volume will come out, so it will be V2 into P3 minus P2. So for this, it will be volume will be V2 into P3 minus P2 is the change in pressure. So the total work input for a vane type of a compressor within a vane, for a single vane, if we have a single vane, in that case it will be given by this W12 plus W23. If we add both these work, so it will be given by gamma upon gamma minus 1 P1 V1 P2 upon P1 to the power gamma minus 1 upon gamma minus 1, brackets closed, plus V2 into P3 minus P2. So this is the total work done if we have a single vane. And if we have n vanes, so we will multiply this equation with capital N, where capital N is the number of vanes on the drum, the central rotating drum. Okay, this is clear. Okay, now the efficiency of a vane compressor, it is given by work input for constant volume compression divided by the total work input. So this means that how much work we have done during the constant volume compression process divided by the total work input during both the compression processes. So it will be given by this equation, that is V2 into P3 minus P2 divided by the total work done, that is the sum of the adiabatic work input plus the isochoric work input. So this is your efficiency of a vane compressor is there. Now the advantages of using a vane type of a compressor, these are that it requires less work input compared to the roots blower for the same capacity and pressure. It can deliver up to 150 meter cube per minute, and it can achieve a maximum pressure ratio of 8.5 as compared to that of a roots blower. Roots blower's compression ratio was maximum was 3.6, but in this case of a vane type compressor, we can achieve more pressure ratio, that is 8.5 is there. Now vane type of compressor, it can run at a speed of 3000 rpm. They are used as superchargers for IC engines, and also for the supply of compressed air for a cupola furnace. Now, cupola furnace is one that is used for the distillation of the crude oil. Okay, so in that the compressed air supplies more amount of oxygen for the combustion of fuel inside a cupola furnace, and for supercharging of IC engines. Now we know that what is supercharging of an IC engine. Supercharging is when we are burning more amount of fuel, that is we are moving at a very high speed. So in that, to achieve that very high speed, we need more power. So for achieving more power, what we need is we need to burn more fuel. Now for burning more fuel, we need more amount of oxygen. Now, more amount of oxygen can be achieved by compressing the air. If we compress the air in the same volume, more amount of oxygen can be supplied. So that compressed air is supplied for the IC engines that we use in high speed cars. So we use this vane type of air compressor for supplying the compressed air for supercharging of IC engines. Now, next advantage is they are portable and are used at construction sites also. Now at the construction sites, we can use these types of vane type of compressors for operating pneumatic drills, for operating pneumatic hammers, for operating pneumatic vices. So all these equipments can be pneumatic means those equipments that operate on compressed air. Okay, those are pneumatic items. So this is your vane type of a compressor. Okay, next type of compressor in line is your Lisham or a screw type of a compressor. Now as we see in the bottom diagram here, the main parts, this black outer, this is the outer casing of the Lisham type of compressor. And in here you can see that there are two types of rotors are there. Okay, the one on the top, it is known as the auxiliary rotor, or it is having these flutes inside. These grooves are known as flutes. Okay, this is also known as a female rotor. And on the bottom side you can see that this is called a male rotor. It has lobes on it. So we have a female rotor and the male rotor. The lobe of this bottom rotor or the male rotor, it fits into these flutes of this auxiliary or the female rotor is there. Okay, so now on the left hand side you can see this arrangement, the cut section of this type of a compressor, that is your screw compressor is shown. Now again in this type of compressor, now one of the compressors, one of the lobes, this is operated with the help of a shaft, and then a shaft is connected to the motor. So one is the driver and the other is driven with the help of gear system is there. So the gears, so again if one rotates in the clockwise direction, the other will rotate in the anti-clockwise direction. Okay, so screw compressors, they are equipped with two mating helically grooved rotors housed with a cylindrical casing equipped with inlet and discharge ports. So it will have a inlet port and it will have a discharge port also. The main rotor or the male rotor, it is the driven it is driven by, so it is a driver, it is driven by an engine or electric motor. About 80 to 90% of the energy received at the coupling gets converted into pressure. So the efficiency of this type of compressor is high. So 80 to 90% of the energy that is supplied, it gets converted into your pressure. Now, if we look at the working part, as the rotors rotate, if you see here, you can see that this diagram here, it will be more clear. Now, this is the inlet part where the blue air is coming in, and on the other side, on this side, on the left hand side, you can see the red air that is coming out is the compressed air. Now, when the air comes inside, it gets trapped between the flute and the lobe of the two rotors. As the rotors, they are made helical, so as they move, this trapped air starts to move in the forward direction. Now as it moves in the forward direction, the mating of the male and the female lobe, what it does is it reduces the volume of air. Okay, so as the volume gets reduced, the air gets compressed, and this compressed air is then as this movement of this, you can see the air, it is getting trapped, it is moved in the forward direction as these both rotors, they rotate. Now as they rotate, it, because of this helical action, the air trapped inside, it gets, you see here, it becomes purple and then red, so it gets compressed, and then this compressed air is delivered out through the delivery side of the compressor. Okay, so this is the working of a Lysholm type of a compressor. So here, if we see here, as the rotators rotates, the air is drawn through the inlet port and it fills the space between the male lobe and the female flute. As rotors continue to rotate, the air is moved past the suction port and it gets sealed in the interlobe space. Now the trapped air is moved axially and radially. So hence the जो trapped air है, that trapped air, it moves axially, means in the axial direction, and also radially along the radius of the rotors also, and it gets compressed by direct volume reduction. Now, because as the enmeshing of the lobes of the compressor progressively reduces the space occupied by the air. So this here you can see that when this here in the diagram here, so as this lobe fully fits in this flute, so the air that is trapped between the flute and the lobe, it gets compressed because of the reduction in volume. Okay, so this reduction in volume, it increases the pressure of air. Okay, so simultaneously oil is, after every suction stroke, some oil is injected inside. So this oil, what it does is it acts as a seal. So it does not allow the compressed air to slip or leak, okay, from the inlet side or towards the outlet side. Okay, so it when the suction it takes place, the air from outside, it gets trapped between the lobes. Okay, at the same time some oil is introduced, so this oil acts as a seal. It does not allow the air to escape. Okay, it can only escape from the exhaust side. Now the working parts of the compressor never get severely operating temperatures, because the oil that is introduced, it acts as a coolant and it absorbs the heat that is being produced because of the compression of air. Okay, as you know that when we compress air, the volume reduces. With the reduction of volume, the pressure increases, and also with the increase in pressure, the temperature of air also increases. So the compression, it increases the temperature of air. Now the oil that we introduce inside, it absorbs that heat. Okay, now this is the working of the Lysholm compressor. So this on top, you can see that this sequence of diagrams, it shows like the air comes in, it gets trapped between the two male and female rotors, and as it rotates, so one rotates in the clockwise direction, other rotates in the opposite direction. So this, what it does is it compresses this meshing, it compresses the air, and then this compressed air is delivered from the discharge side. So here you can see the actual diagram or the cut section of a lyshom or a screw compressor is there. So here you can see that this is the male lobe compressor, and this is the flute inside the female lobe or the female part of the uh, shaft or the compressor is there. Okay. So this main rotor or the male rotor is driven from this shaft, is connected to an electric motor or an IC engine, and this acts as a the main rotor, and at the back you can see that this gears are there. So this is the driver, and this drives the other lobe is the driven is there. Okay, so that is why they move in the opposite direction. Okay, so this is the actual two lobes of the uh, screw compressor. This is the male part and this is the female part. You can see the flutes here. So they completely fit inside, and because of this fitting, the reduction in volume is takes place. Okay. Next, everybody is clear about the screw compressor. Okay. Next type of compressor is your centrifugal air compressor. Now, centrifugal air compressor is a dynamic type of a compressor. It is not a positive displacement compressor, but it is a dynamic type of a compressor. As we have already discussed in the first chapter, that what are dynamic type of compressors. Now, in dynamic type of compressors, the compression of air does not take place where the air is being compressed against a stationary wall and a moving object. Okay, so we cannot see the actual reduction of volume. So hence, but the reduction of the increase in pressure is achieved in this type of a compressor by playing about with the dynamics of air. So in this case, what happens is how we change the dynamics of air. Now, in this case, we have, if we see any dynamic compressor, it will have a rotor and it will have a diffuser. Okay. Now, in the rotor, what happens is the kinetic energy of air is increased in the rotor part. Okay, the air is stationary outside, it is sucked inside the compressor, and the rotor, what it does is it increases the kinetic energy of air. Okay, now this increased kinetic energy of air is then passed through a diffuser. The diffuser is a stationary part in which what we do is we increase the area. Now, as the area increases, the velocity of air starts to decrease. Now, this decrease in kinetic energy, what it does is it increases the pressure of air, because if you see at the front, the air is stationary, getting slow. Okay, but from behind, fast air is coming inside. Okay. So at the front, the air is slow, and from behind, the air, high velocity air is coming out from the rotor side. So this high velocity air, what it does is it pushes the particles of the slow air, and those particles, when they get pushed, they come closer to each other, and because of that movement where the particles they come close contact to each other, the compression of air takes place. Because of this compression, the pressure of the air increases. Okay, now this is the basic working of a dynamic type of a compressor. This we have already discussed in the first chapter, where we did the difference between the positive displacement compressors and the dynamic compressors. Okay. Now next is the centrifugal compressor. So if we want to introduce a centrifugal compressor, so a centrifugal compressor is what? It is a radial flow. Okay, so the radial flow means the air flows in the radial direction. So that is why the flow is radial flow. Rotodynamic means it is a rotating device. So hence the word roto is there. Dynamic means we are changing the dynamics of the air. So hence it is a rotodynamic. where the rotation of the impeller inside the centrifugal compressor, it increases the kinetic energy of air. So hence, because of the rotation, what is happening is the dynamics of air, they are changing. Fluid machine. So in this, what we are using air. So air is a fluid. So hence, it is a fluid machine. So the proper, you can say the terminology to define a centrifugal compressor is radial flow rotodynamic fluid machine. Okay. So that this can be another name for a centrifugal compressor. Now the energy, that is mechanical energy, that is imparted. Now this is, rotor, it is rotated with the help of an external agency, usually a motor. Okay, so this mechanical energy that we impart from outside to this machine to increase the, it increases the total energy of air, of the fluid, and this increase in total energy gets converted into increase in static pressure of air. Okay. So in this, the advantage of this type of centrifugal compressor is it has lesser vibrations and less noise. Okay, the delivery of air is very high. We can achieve around 3000 meter cube of air per minute. Okay, so the delivery of air is high. So where the applications are like we need high capacity of air, so we can use centrifugal compressors there. Okay. Now it is a continuous duty compressor. So means the supply of air is continuous. So that is why it is a continuous duty. It has few moving parts and is particularly suited for high volume applications, especially where oil free air is required. So hence, as we have seen that in the case of a lysham or a screw compressor where oil is supplied. Okay, now in that case, in a screw compressor, the oil gets mixed with the compressed air, and we get a compressed air mixed with oil. Okay, uh, obviously in lysham compressors we use strainers where we separate the compressed air from the oil. We use oil filters, but still some amount of oil it goes in the form of fumes, it goes with the compressed air. So in the rotary compressors that we have discussed previously, some oil gets mixed with the compressed air, and the air that we compressed air that we get is not oil free. But in the case of a centrifugal compressor, the air that is supplied, the compressed air that is supplied, it is oil free air. So that is another advantage of using a centrifugal compressor. Now, if you look into the construction part of the centrifugal compressor, so it has basically three parts. The first is the outer casing, that is stationary. Second is the rotating part. This the first diagram you can see. This is the impeller. This is the rotating part of the centrifugal compressor. It is also known as the impeller. This impeller, what it does is it rotates. The shaft is connected to the motor, and this impeller rotates. The rotating of this impeller, it scoops in air from outside, and when the air moves along the profile of these blades, you can see the blades on top of this impeller. So as the air moves through these blades, because of this impeller is rotating at very high speed, the kinetic energy of the air, it increases when it moves from the center towards the outer tip of the blade. So this increases the kinetic energy of air. So impeller, what it does is it increases the kinetic energy of air. So there are two types of impeller arrangements are there. We can have a single sided impeller, where this example is a single sided impeller. If these blades are also available on the back side of the impeller, okay, so we will have a double sided impeller. So we can have a single sided impeller and a double sided impeller, okay, depending upon our requirement, that how much amount meter cube of air we are needing. If we need more air, we can go for a double sided impeller. If we need less air, we can only go for a single sided impeller. Now after the rotating part, there is the diffuser part is there. Now these diffuser blades, they are fixed blades, and they are of diverging passage. Diverging passage means at the inlet the area of cross section is low, and as we move towards the outlet, the area it increases. Now this increase in area results in decrease in the kinetic energy of air, and results in the increase in static pressure. Now here is the side view and the front view of this type of a compressor. So here we have this is the impeller blade, white. This one is the impeller blade. It is attached onto the hub. This is the hub of the impeller, that is the hashed portion. Okay, this impeller is connected with the help of a shaft to a motor. So this thing rotates, and on this exit side, this is the diffuser blades are there. Now here in the side view or in the front view, you can see this is your impeller blade. Okay, and at the exit from the impeller blade, these blades are the diffuser blades are there. Okay, from the diffuser blades, the air that is compressed, it moves into this volute casing, and from the volute casing, this is discharged into the exit or into the discharge port or the outlet of the impeller. Okay, so if we look at the working, so this portion, this is the inlet. So this inlet, if you see from the front view, it looks like an eye. So hence it is known as the eye of the compressor. From the eye of the compressor, the air goes inside. Okay, and it moves through the blades. As this impeller is moving at a high RPM, the air, when it moves along the blades, it increases its kinetic energy. And this increased kinetic energy air, when it passes through these diverging blades or the diffuser blades, the kinetic energy gets reduced. This decrease in kinetic energy gets converted into pressure. So the pressure of air increases. So this is the basic working of a centrifugal compressor. These are the blades. Now these blades, you can see that at the inlet, these are made little curved are there. So here you can see these blades are curved. So these blades are made curved so that they can scoop air while they are moving. So they can suck air inside or scoop air inside. Okay. Because the atmospheric air that is there, it is stationary outside. So we need to have a process in which this air is sucked inside. Now this sucking of air takes place if we rotate the impeller. These curved blades at the inlet, they scoop air inside. Just in the case, or just as we have a fan that we use in our rooms. So fan blades, if you see, they are a little curved. Now, if the fan is not working, or if it is switched off, the air inside the room is stationary. As we switch on the fan, what happens is the fan starts to rotate. With that, the blades, what they do is, because they are made curved, they scoop air. Okay. And then as the air passes onto the profile of the fan blade, it gains in kinetic energy. Okay. Now this high kinetic energy air is then pushed in the downward direction, and as we come in contact with this high kinetic energy air, this air, what it does is it gives us a cooling effect. The same is the working principle for this impeller blades of the centrifugal compressor. Now, if we look into the working part, from the eye, the air enters. This we have already discussed. So, eye से क्या है? Air अंदर आएगी. So this is the eye. From this, the air is entering inside. As it comes in contact with the rotating blades of the impeller, the kinetic energy of air increases. After that, when this high kinetic energy air passes through the diffuser blades, the kinetic energy gets converted into pressure. Okay, and then through the housing, the high pressure air is discharged from the outlet port. So this is the working. Now here you can see that the air is entering along the axis of the this impeller blade, but this air is discharged at 90 degrees. So that is why this is known as a radial compressor, because the air changes direction through 90 degrees. So air enters at say along the axis, but it exits the impeller in perpendicular direction. Hence, that is why it is known as a radial flow compressor. Okay. So this is the working of a centrifugal compressor. Now here in this diagram, if we see that there are two curves are there. This curve is V is for the velocity curve, and the other curve P is for the pressure curve. And there are two parts here. The first is in between these first two dotted lines is the impeller part, and then between the other two dotted lines is the diffuser part is there. Now inside the impeller, if you see that inside the impeller, what is happening? The velocity is increasing. Now because of this increase in velocity of air, uh, the pressure increase also takes place. How this pressure increase is taking place? Now, as the air that is entering the compressor, okay, now it is at lower velocity, but as it moves away towards the tip of the impeller or the exit of the impeller, the velocity, the absolute velocity is increasing. But if we look into the relative velocity, okay, now in this case, the okay. Now, in this case, if we look at so there is an increase in pressure. It takes place inside the impeller blades also. Okay. Now, uh, okay. So here we can see that with the velocity is also increasing and the pressure is also increasing inside the impeller. Now, there is some. If you have seen this diagram here, for a diffuser. So in between the impeller blades and the starting of the diffuser blades, there is this small clearance is there. So this clearance is provided. Now this clearance, what happens is in this clearance, uh, the uh, velocity, uh, it remains almost constant, but the pressure drop takes place. Small pressure drop takes place in this clearance. Now, again in the diffuser, after that is the diffuser blade. Now, in the diffuser blade, because it is a diverging cross section, so the area of cross section is increasing, the kinetic energy or the velocity of air is decreasing. Now, this decrease in kinetic energy is getting converted into increase in pressure energy. Now, you can see here in the impeller, pressure is increasing, and in the diffuser, pressure is also increasing. But if you look into the velocity part, in the impeller, the velocity is increasing, but in the diffuser, the velocity is decreasing. Okay. So this, so pressure is increasing both in the impeller and the diffuser part. Okay. So now this look, if you look into the velocity triangles for the centrifugal air compressor. So here in the middle we have the uh, blade of the centrifugal compressor, which is moving at a blade velocity of u in this direction. Now the air is entering along the axis, so it is entering. You can say it is entering at 90 degrees. So alpha, the inlet angle of that is the absolute velocity, it is 90 degrees. So it is entering at 90 degrees towards the blade. Now the blade is moving in this direction, okay, and the air is moving in this direction, 90 degrees. So the relative velocity with which the air actually enters the blade is VR1. VR1 is the relative velocity. This is the relative velocity because the air is the absolute velocity of air is perpendicular to the blade velocity u. So by using the relative concept, the air actually that enters in is with the relative velocity, and this relative velocity of air at the inlet makes an angle beta with the your inlet blade velocity u1. Okay, and at the exit side, okay, now at the exit side. If you look here, the air that uh, exits at the angle uh, that is at the angle of the exit angle of the blade. This will be the relative velocity VR2. Okay. Now VR2, this is VR2. Now the blade is moving in this U direction. Okay. Now and U2 is the blade velocity at exit. Now, if you see here, this blade is actually installed or it is attached onto the hub. It's there. Okay. Now hub, this blade is moving at an angular velocity of say omega. Okay. Now from the center of the hub, the radius at the inlet is small and the radius at the exit is more. So the blade angle or the blade velocity, sorry, the blade velocity at the inlet, it will be given by the radius R1 into U. Okay. And the velocity at the tip or the exit of the blade, it will be given by radius R2 into U, into omega. Okay. Now R1 is small and R2 is big. So this means the blade velocity at the inlet will be small. So that is why U1 is small. And the blade velocity at the exit is big. So it will be given by R2 omega. So U2 is big. Yeah. There U2 is the blade velocity at the exit. Because the radius at the tip is more and the radius at the inlet is small. So the blade velocity is there. It is smaller at the inlet to the blade. And this blade velocity is large. U2 is large at the exit. Now, if we look at the relative velocity concept, and this is the VR2, this is your U2. So if we join these 2 points, that is this exit point and this U2 end point, so the velocity that we get is the V2 velocity. This is the absolute velocity at the exit. So the angle that the absolute velocity makes with the blade velocity or the horizontal is theta, and the angle that the relative velocity makes with the horizontal is phi. Now this blade velocity will have two components. Vf2, it is the flow component, and Vw2, it is the your whirl component is there. Okay. Similarly, the V1 here, the inlet absolute velocity at the inlet, it will have two components. Uh, so it will have the vertical component that is known as VF1. Now VF1, if we see here, it will be equal to, because the vertical component is always V1 sine alpha. Now in this case, alpha is 90 degree. So it becomes, so V1 becomes equal to VF1. Okay. And the horizontal component will be VW1. It will be equal to V1 cos alpha. Now cos 90 is 0. So hence the, in this case, where the inlet angle alpha is 90 degrees, the whirl component is 0 in the case of a centrifugal compressor. So these are the inlet and exit velocity triangles for a centrifugal compressor. Next, if we look into the centrifugal compressor, the various, if we look at the working of a centrifugal compressor, uh, the working here is, if you see here, the graph at the bottom, this graph is between, on the horizontal axis, we have the mass flow rate of air, and on the vertical axis, we have the pressure ratio. Now, as the you can see that when there will be when the compressor is to be started, okay, and if we see that we assume that the delivery valve is fully closed. Okay. Now the centrifugal compressor is stationary; it is not moving, it is not running, and the delivery valve is closed. Okay. So there will be some air that is trapped inside the compressor vanes. Now, as we start to run the compressor, the air inside the impeller or inside the compressor, it will gets compressed. That point is given by point E. Okay. So the air inside the compressor and the delivery valve is closed. So air inside the compressor, it will be compressed. Okay, and that point is given by point E on this graph. Now, as we gradually start to open this exit valve, so the air starts to flow through the discharge valve, and the mass flow rate of air, it starts to increase. So as we start to gradually open the exhaust valve, the mass flow rate starts to increase. So we start to move from E to point D. So this curve, it shows us the increase in both mass flow rate from E to D and the pressure ratio also. The pressure ratio is also increasing. So at a certain point, point D is achieved, where uh, at this mass flow rate, the maximum possible pressure ratio is attained. So D point is the maximum possible pressure ratio that can be achieved inside a centrifugal compressor. If I again start to open the delivery valve, the mass flow rate again starts to increase, but beyond point D, what happens is the pressure ratio starts to decrease. So as I start to increase, open the delivery valve, I reach point C, I reach point B, and then I again start to increase, open the delivery valve, and a point A is reached. Okay. Mass flow rate, as it is increasing, the pressure ratio is decreasing. So at point A, what happens is, at this point A, the maximum possible mass flow rate is. Okay. So at this point A, maximum possible mass flow rate is achieved at this point. Okay, it is reached. Beyond this point, if I again start to open the delivery valve, the increase in mass flow rate does not take place. So it is a vertical line. The mass flow rate does not increase. This point, where the maximum possible mass flow rate is reached, this point is known as the choking point. So this is your choking point, where the maximum possible mass flow rate to a centrifugal compressor is reached. This point is known as the choking point of a centrifugal compressor. And now, in this graph, if we see that D is the point where the maximum possible mass flow rate is reached, and A is the point where the maximum, at D is the point where the maximum pressure ratio inside the cycle is reached, and A is the point where the maximum possible mass flow rate is reached. So this means I can operate my centrifugal compressor between D and A. D और A के बीच में I can only run my centrifugal compressor. So DA, in between DA is my working point. DA के बीच में point C, point B, these are my working points where the working of a centrifugal compressor can take place. Now we cannot go in the this zone E and D. Okay, ED zone I cannot go. Okay, we will see what happens if I go into ED zone here. Here it is this zone results in this problem, that is surging. So this topic is surging. Now suppose we are at point B, uh, where the mass flow rate is given by this horizontal line, and the corresponding pressure ratio I can see here. Now as I start to close the delivery valve, the mass flow rate starts to decrease. Okay. So I start to move in the backward direction. So I reach point C. Again, I start closing the delivery valve. What happens? I go backwards and I reach point D, where the maximum possible pressure ratio for the cycle is achieved. Again, what I do is I uh, close the delivery valve. In this point, what happens is I reach this zone ED is there. Okay. Now in this ED zone, what happens is the air on the others on the right hand side of the delivery valve is at high pressure, and the air on the left hand side of the delivery valve is at low pressure. This means the air that is inside the compressor is at low pressure, and the air on the delivery side is at higher pressure. So the air, what will happen is it will start to move in the backward direction. So the air starts to move from the delivery side into the compressor side. Okay. So backflow of air takes place. So after sometimes what happens as the impeller is moving, the pressure again starts to increase, and the air starts to get delivered into the delivery side. After sometimes what happens is again the pressure on the delivery side it increases, okay, because of reduced mass flow rate, and the backflow of air starts to take place. Now this situation of instability, where sometimes the air is getting delivered, sometimes backflow of air is taking place, again for some time the air is getting delivered, again the backflow of air is taking place. So this instability of the compressor, this situation, it is known as the surging. So we cannot operate our centrifugal compressor in this ED curve. So in this ED curve, what happens? Surging takes place. Okay, I cannot operate my compressor at point A because this is choking point. Okay, and the mass flow rate at the choking point almost reaches one. The pressure ratio almost reaches one. That is, the suction pressure becomes equal to the delivery pressure. Okay. So the only curve in which my centrifugal compressor can work is in between D and A. Okay, not onto the left hand side and not beyond. So this is my working of a centrifugal compressor. Okay, what are the effects of surging on the centrifugal compressor? Now, the rapid flow of pressure oscillations causes process instability. So instability of the process of compression is achieved because the air is oscillating. It is for some time it is getting delivered, for some time backflow of air takes place. So the instability of air delivery is there. So this surging, it causes the increase in temperature of air. Okay. Uh, and then third is the tripping of compressor takes place. Tripping means the supply of compressed air is stopped. So that is tripping of air. Okay. Now this instability also causes mechanical damage to the compressor parts. Okay. The radial bearing, okay, because of surging, it might get damaged. Thrust bearing uh, also might get wear and tear. Okay, the rubber seals, they also might get damaged because of the oscillations and the vibrations that are produced because of this surging. Okay, stationary and rotating parts contact if thrust bearing is overloaded. Okay. Now if the thrust bearing is overloaded, stationary and rotating parts, they might come in contact with each other, and this might cause rubbing of metal parts, and the wear of the parts might take place. So these are the uh, various effects of the surging that takes place on the centrifugal compressor. Okay. Next topic is your pre-whirl. Now, if we talk of the inlet to the centrifugal compressor, okay, the air that is entering. Now, this centrifugal compressors, they are used inside gas turbines and jet engines, and those jet engines and gas turbines, they run at a very high speed. Okay, so if I increase the speed, now if I talk of before I talk of the pre-whirl, there is a new term that comes in that is known as the Mach number. Now Mach number, one Mach, uh, now Mach number, if I define, it is the velocity of air, or the actual velocity of air divided by the velocity of sound. So the velocity of air, if I compare it with the velocity of sound, okay, so I get a Mach number. Now if the velocity of sound, it becomes equal to the velocity of sound, okay, so this means that the value of capital M becomes equal to 1. Okay. So this means that we have achieved Mach 1, or we have achieved the velocity of sound. Now we can calculate the velocity of sound at NTP, that is normal temperature and pressure. At NTP, the temperature is 20 degrees centigrade or 293 Kelvin. Gamma, this velocity of sound is given by under the root of gamma into R into T. Okay. So gamma is 1.4 for air, R is 287 for air. This is standard values. Temperature at NTP is 20 degree or 293 Kelvin. So if I solve this under root, I get the velocity of sound as 343 meters per second. Okay. Now, if the velocity of air it reaches the 343 meters per second, this means we have achieved Mach 1. Okay. Now, if we increase the speed of air beyond Mach 1, so what we do is we uh, have crossed the sound barrier. Okay. So we are going to cross the sound barrier. Now, uh, if we cross the sound barrier, so you might have heard of sonic boom. A sonic boom is created. Okay. Now, this sonic boom is actually a very loud sound that is produced when we cross the sound barrier, and it's like an explosion that takes place. If we cross the sound barrier, it's like an explosion that takes place, and lot of shock waves are produced. So the pre-whirl, that pre-whirl is nothing but what we do is we decrease the angle of air at the inlet. Where the angle at the inlet, we know alpha is 90 degree. So what we do is we reduce that angle from 90 degree. That angle may be between 0 and 90 degrees there. Okay. So by reducing the inlet angle of air, what we do is we avoid this crossing the sound barrier. Now, what are the advantages of pre-whirl? Pre-whirl avoids shock waves formation. It reduces losses which were to be there due to shock wave formation. So we have seen, we have, know that if we cross the sound barrier, shock wave is produced. Now this shock wave is very dangerous for the various parts of the compressor. It might damage the compressor. Now, disadvantage of pre-whirl kya hai? It reduces the required output and it also reduces the pressure ratio. So, if we decrease the angle at the inlet, it will decrease the pressure ratio for the. So, these are the disadvantages of using pre-whirl. Okay. Now, here in this diagram, you can see that if you see this solid triangle, this is for the actual inlet where the angle is 90 degree. Okay. In this case, what happens is the value of C1, uh, that is uh, this is the C1, that is the absolute velocity at inlet, and this solid line, this is CR1, that is the relative velocity at inlet. Now, if I reduce this angle from 90 degree to alpha dash, now this angle is less than 90 degree. So you can see that this gets the C1, that is the absolute velocity at inlet. Uh, the direction it changes, and you can see that the absolute velocity at inlet, it is increasing, it is getting increased, but the relative velocity at inlet, it is getting smaller. So यहाँ पे relative velocity is given by this line, so this line is bigger as compared to this dotted line of CR1 dash. So the relative velocity with which the air now enters into the blade, it is reduced. So we have achieved the reduction in the velocity of air that actually enters the uh, impeller blades. So this is your pre-whirl. So pre-whirl is nothing but the angle that is given to the air at inlet, and that angle is less than 90 degrees. So by using this pre-whirl, you can see that from the Euler's work. Okay, now if I have given this angle to the uh, air that is going inside, if I have reduced this angle, so in this case we also get the whirl component CW1 is there. So when the angle is 90 degree, CW1 is 0. But if I give an angle that is less than 90 degree, so I will get CW1. Now from the Euler's work, that is CW2 into CB2 minus CW1. So this minus, what it does is it by using pre-whirl, we are able to decrease the work input or the work input from the motor that we are using to run the turbine. So we are saving the work, Euler work, or the work done on the compressor Okay, so here Euler work with the pre-whirl is given by this equation, and without pre-whirl, where the angle is 90 degree, it will be given by CW2 into CB2. So this work is greater as compared to the work done because of the pre-whirl. So hence, by using pre-whirl, we can save the work input. So that is all for this session.